Welcome. In this video, we will explore the intersection of medical research and deep learning. Today, we will be showcasing how we at Codersarts have successfully replicated a critical research paper that focuses on classifying ECG signals into 4 distinct categories. This is not just an academic exercise, it's a step forward in improving healthcare through technology. So let's start with the problem statement. We all know that cardiovascular diseases continue to be a leading cause of death worldwide. Among these, atrial fibrillation, or AF in short, is particularly dangerous. Early detection is crucial to prevent severe complications, but it's often challenging due to the subtle nature and variability of ECG signals. In this video, we will delve into the implementation of a research paper that tackles this issue by using deep learning to classify ECG signals. The research paper that we focused on addresses this critical issue by developing a method to classify ECG signals into 4 distinct categories, which are as follows. The first category is the normal category, where the ECG signals are going to be normal. The second category, which is our primary focus, is the atrial fibrillation category. Then the other 2 categories are the other conditions and the noisy signals. This classification is essential for the early diagnosis and effective treatment of heart diseases. Our aim is to replicate this research paper, which is named Convolution Recurrent Neural Networks for Electrocardiogram Classification by Martin Zillman and others. And by doing so, we wanted to validate the model's effectiveness, contributing to the broader efforts in improving heart disease detection and ultimately healthcare outcomes. You must be wondering, why does this matter? Accurate classification of ECG signals allows for timely medical interventions, potentially saving lives. This project showcases the immense power of AI and machine learning in addressing real-world health problems, particularly in the early diagnosis of conditions like atrial fibrillation. Now, let's dive into the data set that forms the foundation of this research work. We worked with a comprehensive ECG data set consisting of thousands of signals categorized into 4 classes: normal, atrial fibrillation, other conditions, and noisy signals. Each signal is a snapshot of a patient's rhythm, and the challenge was to train a model to accurately classify these signals. This dataset is rich in variety, making it perfect for training a robust model. Let's get into a little bit more detail about this dataset. So this dataset was generously provided by AliveCore. These recordings are integral to this research, giving us the data needed to train and validate our model. The training set consists of 8,528 single-lead ECG recordings, each lasting between 9 seconds and just over 60 seconds. This rich data set allowed us to capture the nuances of various heart conditions. On the other hand, the test set contained 3,658 recordings. The ECG signals were sampled at 300 Hz and bandpass filtered by the AliveCore device, ensuring that we work with high quality data. These recordings are provided in MATLAB v4 WFDB compliant format, which includes both the .mat file containing the ECG and a .HEA file with waveform information. As we move forward, we'll explore how we use this data to classify the ECG signals into 4 distinct categories. Understanding the nature and structure of the dataset is very crucial for any project. And now that we are familiar with the dataset, we can move on to the next section, where we are going to discuss the steps that we have taken for the implementation. Our replication process followed a structured approach. The first step was data pre-processing. In here, we prepared the raw ECG data for model training. This involved cleaning the data to remove noise and artifacts that could skew the results. Next, we normalized the ECG signals to ensure consistency across the dataset, which is particularly important given the variability in recording conditions. We also had to address the challenge of differing lengths in ECG recordings as the duration varied from 9 seconds to over 60 seconds. To handle this, we standardized the input lengths by padding shorter sequences and truncating longer ones, ensuring uniform input to our models. The next step was model implementation. For model implementation, we initially followed one of the architectures proposed in the original paper, which combined convolutional neural networks, CNN in short, with long short-term memory networks, that is LSTM. This architecture is effective in capturing both spatial and temporal features from the ECG data. However, we were not able to achieve the exact results as that of the paper, so we also experimented with a more advanced architecture, which is a CNN combined with a bidirectional gated recurrent unit, that is BiGRU, with an attention layer. The addition of the attention mechanism allowed the model to focus on the most relevant parts of the ECG signals, potentially leading to better performance. The next step was to split the data into train and test set. This step is crucial to ensure that our model learns from the subset of the data and is then evaluated on unseen data, allowing us to measure its true performance. The split was done in a way that preserved the distribution of classes across both sets, ensuring a fair evaluation. And finally, the last step was evaluation. We evaluated the performance of both models. We assessed the accuracy and the F1 score of the models on the test data, comparing these metrics with the results reported in the original paper. This comparison helped us gauge how well our models replicated the findings and whether our advanced model offered any performance improvements. This structured approach, from data pre-processing to rigorous evaluation, was essential in replicating the research paper and exploring potential enhancements. And with this, we are ready to move to the next section where we are going to discuss the results. The results were promising and our model demonstrated a good level of accuracy in classifying the ECG signals. In the image above, we can see the results from the paper. We had chosen to replicate the CRNN model, which is nothing but the CNN plus LSTM model. And for this particular architecture, the accuracy that is achieved in the paper is 82.3% and the F1 score is 79.2. In our implementation, we were able to achieve an accuracy of 79% for the same architecture. While this accuracy is not exactly the same as that in the paper, but still it is fair enough. And to improvise further, we tried several different architectures, out of which the best model came out to be CNN plus BiGRU with attention layer. With this model, we were able to get an overall accuracy of 82.18%, which is almost the same as that of the paper. And in the graphs in here, we can see the learning curves for the training and validation accuracy for both these models, that is CNN plus LSTM and CNN plus BiGRU with attention. Moreover, we can also see some screenshots of the results from the implementation. Here it is validated that with CNN plus LSTM, we achieved an accuracy of 79%, whereas for the CNN plus BiGRU with attention model, we got the best accuracy of 82.18% after hyperparameter tuning. So these were the results. This replication not only validated the findings of the original paper, but also highlighted potential areas for further improvement. By successfully replicating this study, we have taken a significant step towards making AI-driven healthcare solutions more reliable and accessible. So, if you are inspired by this demonstration and would like to leverage our expertise for your own research or projects, don't hesitate to reach out to Codersarts via our email address, which is contact@codersarts.com, and you can also connect with us via our website, which is www.codersarts.com. Whether you need help with data replication, machine learning models, or any other technical challenge, our team is here to support you. Please like, share, and subscribe for more insights into how technology can transform Healthcare. You can find our Facebook, Instagram, and LinkedIn handles in the description box down below. Thank you.